Hello everybody, this is the video clip for chapter 3 and we still on the application of a derivative. Okay, so for this video clip we are going to see how derivatives affect the shape of a graph. Okay, and by derivative we actually talking about the first and also the second derivative. Okay, so the first derivative we already see that if your f prime is positive, then it means that it is increasing. Okay, and by increasing you see that okay, the graph will going up. Okay, maybe like this, or it may be like that, or it can be like a straight upward, like going up like that. But if your f prime is negative, okay, then it means that your function is decreasing, and by decreasing it means that your graph will going down. So it may going down like this, it may going down like this one, or it may go straight down like that line. Okay, so it depends. Now the second derivative will determine clearly, okay, the what should I say clearly, but we can say that it more details. Okay, it will determine more details on the shape of the graph. Okay, so the shape of the graph that we are going to consider is the so-called concavity. Okay, so we have two kinds of concavity. So we have concave upward. The concave upward, it means that the curve f will lie above the tangent line at the point C. Okay, so for example, if you're talking about this one, okay, if this is the point C, then this is the tangent line, right? If this is the point C, this is the tangent line. Okay, all these are tangent line to this curve, and you can see that all the tangent line go below, you see, go below the curve. Okay, so it means that along this interval, okay, along this interval, it is the interval of concave up. Okay, so concave up, it will look like a U shape. Okay, and a U shape like this will give you a what, a valley, you see. And then the next one about a concavity is a concave downward. Okay, so it means that if your curve y equals to f lies below a tangent line. Okay, so for example, look at this one. If this is your point C under consideration, here is the tangent line, there's a tangent line. Okay, so all those tangent line they are all above the curve y equals to f, you see. So it means that on this interval, okay, the concavity become concave downward. Okay, or sometimes we just say concave down. All right, and the concave down, it look like this one. Okay, it's look like a hill. Okay, so it means that if you have a concave down, it seems that you have a hill. So this one is one of the most confusing, but if you draw a graph together with the terminology, that will help you a lot. Okay, so by saying down, it determines a hill. By saying up, it determines a valley. Okay, so to see the concavity, we can use the derivative as well, but this one, it is the second derivative. So why the second derivative can come to play with this concavity? This one, look at this tangent line. This is the tangent line that it is slope is negative, right? But then if you look at this one, okay, the tangent line become horizontal. Okay, so the first one, the tangent is negative, the slope. This one, it is horizontal, so the slope is 0. But then when you looking at this one, still in the interval that concavity is upward, right? This one is positive. So what is the change of the slope of the tangent line? It changed from small, right, negative, to a larger value which is 0, and then go positive. You see, from small to large. So the changing, okay, it changing is going up, right? The changing is increasing, you see, from small negative value to a 0 value and to a positive value. So this one, it means that in this interval, okay, when it is concave up, the slope of the tangent line, okay, change from small to large. Okay, by small to large, it means that it is increasing. Okay, it means that it is the changing, it is increasing. Okay, so the slope is a what? The slope of the tangent line is f prime, right? And when you say that your f prime is increasing, what does this mean? It means that a derivative of the f prime is positive, right? And a derivative of f prime is simply f double prime. Okay, so if you can solve for the interval that your f double prime is positive, then it means that over that interval your f concave upward. Okay, so on a contrary, if you look at this one, okay, over the interval that your concavity is downward, you see that this one slope is positive, and then a slope becomes 0, and then a slope becomes negative. So it means that the slope, okay, of the tangent line for this interval, okay, changes from what? From large, right? Because it is from positive to negative to small. Okay, so what does this mean by from large to small? So it means that you have decreasing, right? You have the slope is decreasing, is going down and down, right? Smaller and smaller, decreasing. So again, the slope is a what? The slope is your f prime, and your f prime is decreasing. It means that a derivative of your f prime is negative. So a derivative of the f prime, it means the second derivative f double prime. So if you can solve for the interval that your f double prime is negative, then it means that your f is concave downward over that interval. Okay, so this is another tools, right? The first two that we have, it is your f prime positive, then your f is increasing, your f prime is negative, then it means your f is decreasing. So this one is about your f double prime will determine a concavity. Okay, so a point, okay, a point P on the curve is called an inflection point if your f is continuous there. Okay, so it means that first of all, this point P must be inside the domain. Okay, must be inside the domain of a function f under consideration, and then the curve change a concavity from upward to downward, or the other way around, from downward to upward at this particular point P. Okay, and for example, this one, you may be able to see that this point here, the C here, is the point that change a concavity, right? From this one upward, okay, passing this point, it start to go downward. Okay, so here is the inflection point. Okay, and how we determine the inflection point, we have a theorem. If your x equals to c is going to be an inflection point, then it means that your f double prime at that point will be 0, or your f double prime at that point does not exist. Okay, look at it carefully again. This theorem is a P implies Q. So this means that if this one is already known to be inflection, then all these properties may occur. Okay, however, the other way around is not. So we have a remark saying that if your f double prime at that point equals to 0, then we may not be able to conclude that the point C is an inflection point of a function f. Okay, we need to check whether the sign of the concavity change or not. Okay, for example, if you're looking at x fourth, so your f prime is 4x cubed, and then your f double prime is 12x squared. Okay, and this one will equals to 0 whenever your x itself equals to 0. But if you look at the x fourth, actually the curve look like this, which always concave up, right? It always concave upward. Okay, so your 0 is not the inflection point. Okay, however, again, to find the inflection point, we were looking for this kind of point, okay, that your f double prime equals to 0, or your f double prime at that point does not exist. So all this is only a candidate, again, okay, a candidate for what? For inflection point. You need to really check the sign. Okay, so it's look like the one that we used to find for finding the local max or min, right? You find this one, is it the f prime as c equals to 0, or your f prime as c does not exist, right? But all these are just a candidate. Okay, but the candidate for the local max and min has a name, which is a critical number, but this one has no name. It's just a candidate. Okay, no special name for it. Are we all right? So first of all, let us go through some example here. If you have your f like this, you find the interval of concave up or concave down, and also the inflection point. Okay, so here your f prime, it is what, 12x cubed minus 12x squared, and this one actually you to find the inflection or the concave up or concave down, you need to find f double prime, right, which is 36x squared minus 24x. Okay, and then to determine, you are going to do a factorization, which is 12x, right? That's the common factor, and 3x minus 2. Okay, and then you just make it equals to 0. Why is that? Because this one exists for each and every x in the real number. So the only the only candidates for the inflection will be the one that your f double prime equals to 0. So it means that your x can be 0 or 2 over 3. Okay, these are the candidates. All right, so you are going to look for the sign. This one is the sign of your f double prime, all right, at 0 and 2 over 3, whether it changed or not. Okay, so here you plug in 1, you got 3 minus 2, which is positive. This one is also positive. So here in this interval, it is positive. You can plug in 1/3. Okay, this one becomes a what? 1 minus 2, which is negative. This is positive, so the whole thing becomes negative. And then this one you can plug in -1, so you have negative, and -3 minus 2, which is -5. So together will be positive again. Okay, so it means that your f is concave upward over the interval from -infinity to 0 and the interval from 2 over 3 to infinity. Okay, because these two interval, the sign of your f prime is positive, and it is concave downward, okay, it is concave downward over the rest of the interval, which is from 0 to 2/3, because over that interval your the sign of your f double prime is negative. Okay, and you can see immediately that the candidates here and there, okay, you see that the sign of your f double prime changed at these 2 points. So it means that this 2 point is not only the candidates, but it's also a what, the inflection, okay, occurs here. Okay, and if you need to find the inflection point, okay, you need to find both x and y. So if your x is 0, this one is f at 0, and if your x is 2/3, this one is your f at 2/3. Okay, so for this one it is not that difficult, right, that this is also 0. But if your f is 2/3, then you may need to, you know, work out a little bit, okay, what you end up with. Okay, all right, so I'm not going to do it for you, okay, which value it is. Are we okay? Okay, and next, if you want to see your f as arctangent of x, okay, now your f prime, it is simply 1 over 1 plus x square, you still remember, and then your f double prime, it is a what, you can use the chain rule, right, which will be -1, and then 1 plus x squared raised to the power -2, and then a derivative of the inside, which is 2x, or it can be -2x over 1 plus x squared raised to the power 2, right? So don't forget that this one's always positive, okay, and no matter your x is, the bottom can be found as a non-zero, right, because you got 1 plus x squared, so it will be non-zero. So it means that your f double prime exists again for each and every x in the real number. Okay, so the only candidates for the inflection point will occur when your f double prime equals to 0, and because your f double prime, it is in terms of fractions, the fraction will be equals to 0 only for the top equals to 0. So it means that your x is 0 as a candidate again. Okay, first of all, it must be a candidate first. Okay, and then you look for the side of your f double prime, okay, passing through this point. All right, so here you can plug in 1, the bottom always positive, right, so the top become -2, so altogether is negative. You can plug in -1, so here is positive, there's positive, so together will be positive. So it means that it is changing from concave upward to concave downward, right? Okay, so it concave up, okay, it is concave up over the interval from -infinity to 0, and concave down over the interval from 0 to infinity. Okay, and that 0 now is not only the candidate, because you see at this particular point concavity change from up to down, so this one is not only the candidate, but the inflection point also occur at this x value. Okay, the inflection occurs here. So if you want to find the inflection point, okay, so it will be 0 and the arc tangent of 0, okay, and the arc tangent of 0 is simply 0 as well, okay, which is 0 0, okay. All right, so now for the first example you have been go through with your f prime, right, and we hope that you still know that this one it is like 12x squared. This one we already did it, right, and then x minus 1, and the sign, okay, from 0 to 1 it look like that, right, okay. So this one is the sign of your f prime. Then what does this mean? And if you combine these two things, then what will help you finding the shape of the graph more clearly, okay. This one as well, if you look at it carefully, you can see that here is your f prime, and your f prime is always positive, right, because the top is a fixed number, positive, and the bottom depends on 1 plus x squared. So it means that, I mean, it will increasing all the way, and with the increasing all the way together with the concavity up and down like this, can you see more clearly what is the shape of the graph? Okay, that is very important. So we would like you, we encourage you to look at it by yourself first. However, later on we are going to go over this kind of problems with you, okay. So let's look at another one. If your f is x and e raised to the power negative x, then your f prime, it is the product rule, right? So it will be the first, okay, it will be the first, and then derivative of the second, don't forget a derivative of the inside, right, plus the second derivative of the first, and then usually you will pull out a common factor first. So you have this one, right, e raised to the power negative x multiplied by negative x plus 1. And now what is your f double prime? So it is again the first derivative of the second plus the second, and then derivative of the first, which is e raised to the power negative x, and then a derivative of the inside. So your e raised to the power negative x can be out, and then this one become x minus 1. So you got e raised to the power negative x and then x minus 2, right? Okay, so this one again, it is exist for each and every x in real number. So the candidate, okay, the candidate happens whenever your derivative, the second derivative, equals to 0. However, this one's always positive, cannot be 0. So the one that can be 0 is only x minus 2. So it means that the candidate is at x equals to 2. This one again, first of all, it must be a candidate first. Okay, then look at the sign of your f double prime. This one, the sign of your f double prime at 2 passing. So now, for example, if you plug in, oh, you cannot be 1, right? It can be 3. So this one's always positive. This is 3 minus 2, which is positive. So altogether, it is positive. You can plug in 0 to be very easy. So you have negative here, you have positive there. So it is negative, okay? So it means that you have a concave down and a concave up here. So at this particular point is the change of concavity, right? So it's not only the candidate, but the inflection point also occurs here, okay, and the inflection point, okay, becomes 2 and f at 2, which is 2 e raised to the power negative 2, right? and concave upward over the interval from negative, 2 to infinity, and concave downward over the interval from negative infinity to 2. Okay, this one's downward. All right, so we again encourage you to look at the side of your f prime. So the side of your f prime will depends on the number 1. Okay, and then if you combine these two information, what can you really see about the shape of the graph, okay, of the curve. All right, so what else that a concavity give? Okay, actually a concavity also saying that if your c is a critical number of the f, okay, and f double prime at that point is positive, then it means that you have what, as we told you before we go to this implication, we should interpret that the f double prime is positive, then it means concave up. By concave up, you got a valley, so this one will be your local, the local minimum will occur here. Okay, a local minimum will occur here, and then by this one, okay, the if your f double prime is negative, then it means that you have a concave down. By concave down, it means that a local maximum or a hill occurs there. Okay, so this one is another test, okay, for you to determine whether a critical number gives you a local max or a local min. However, if your f double prime at that critical number equals to 0, then we cannot conclude. Okay, we cannot conclude anything. Then we need to go back and use the first derivative test. Okay, so sometimes we may see that the second derivative is a little bit easier, okay, because you just determine only the a function value, I mean the f double prime value at one point, okay, and sometimes the first derivative seems to be a little bit difficult, but the thing that is difficult always work, okay, and this one has a limitation. It works only if you can determine whether it is positive or negative, okay, otherwise you don't know. So for example, if you try to solve for this one, we have an open topped rectangular box, okay, so we have a rectangular box like this without the top, okay, so we have only the bottom here and all the sides, okay, with a square base, okay, so this is not that square, right, but let's say this is x and x, okay, and you need a volume, so let's say that the height is y, and you need a volume to be 500 cubic centimeter, so it means that the volume, it is x squared y must be 500, right, the area of the base multiplied by the height. You need to find a dimension that minimize a total area A, okay, of its base and the four sides, okay. So the area that we're talking about, okay, it will be the base and the four sides, okay, without the top, right. So the base, it is a area of a square, which is x and x, and each sides, okay, it will be this one, right, x and y, and also x and y, and also x and y. So it will be what, 4 of x and y, okay. So again, you need to use this relation to get rid of the y, right. So this relation saying that your y is simply 500 over x squared, so it means that your area will be 4x and then 500 over x squared, or it is x squared plus what, 2000, over x, right? Okay, and because this one we have the only thing that your x must be is that your x must be positive, right? And no other conditions. Okay, so it means that we are going to use this function f of x and find a local minimum. Okay, because you need to minimize, so to find a local minimum, so you first find the derivative, the first derivative to find the critical value. So you have 2x and then minus 2000 over x squared, right? Okay, because this one it is simply 2000 and then x raised to the power negative 1. Okay, and then you just simply make it equals to 0, because this one again it is excess for each and every value of x that is positive, right? So the only critical value occur when your f prime equals to 0. So it means that you got 2x equals to 2000 over x squared. So you do a cross multiply, you got x cubed equal to 1000. So it means that your x is simply 10 centimeter. Again, this one is only a critical number. Okay, a critical number. You need to test it. Okay, so previously you test by your f prime, right? So this time, if you test by your f double prime, you got 2 and then plus 4000 over x cubed. Okay, why is it a plus? Because this one is simply 2000 x raised to the power negative 2, right? So to find a derivative, this one will be kicked down, so it will be a plus. Okay, and then you replace your f by your x by a 10. So at 10 it will be 2 plus 4000 over a 10 cube. Okay, and we don't really care about a value, we just know that this one is positive. So by positive it means that the graph is concave upward, and the concave upward it means that a local mean occur. So at this critical a local mean occur here. Okay, and a local mean of what? Of the area of the base and the four sides. Okay, and you just need to find a dimension. So by dimension it means that you just need to find your x, okay, which is 10 and 10, and your y, which is 500 over the x square. So 500 over 10 square, your y becomes 5. Okay, so you got a dimension that you need, okay, to make the volume to be 500 cubic centimeter, but minimize a total area of the box. We good? Okay, so let us stop this video clip right now. Okay, and we are going to consider some other thing that may make the shape of the graph, okay, of a function that we want to sketch is like more clearly, and then we can sketch the graph more neatly. Okay, so we'll see you on the next video clip. Bye bye.